Hi class, welcome to EdVantage. My name is Dr. Scott Adamson, and the purpose of this video is to provide an intuitive way of thinking about a very important mathematical theorem that we'll study in calculus. It's called the mean value theorem. So this is to have you think about what that theorem would mean, and then in later videos you'll see how it's applied to develop other mathematical ideas. So let's start with a context we've seen earlier when we were talking about the development of instantaneous rate of change, the derivative. The context was this. There's a sprinter running a 100-meter race. And this sprinter, we were able to collect data to see where was the sprinter at different time moments during the race. How far was the sprinter away from the starting line? So at time 0, the start of the race, the distance from the starting line was 0 because he's at the starting line. 2 seconds later, 4, 5, 6, 8, and 10 seconds later, the runner was at these locations, distance from the starting line. And what we were examining here is how fast was the runner running at some moment in time. And we examined that by first thinking about this runner's average rate of change. Now you'll notice here in blue, I've written the change in distance over these time periods to make the point that this is not a linear function. So if you look here, from time 0 to time 2, the runner increased his distance by 13.6 meters. But then in the next 2 seconds, his distance increased by 16.8 meters. Now had this been a linear function, those rates of change would all be constant, but this is not a linear situation. Look at the last bit of this race. In this 2-second chunk, from 6 seconds to 8 seconds, the distance increased by 23.2, and in the last 2 seconds of the race, the distance increased by 26.4. So looking at these 2-second increments, we see an ever-increasing amount of distance, change in distance that this runner has accomplished. Also, in the middle here, I had some 1-second intervals, and you can likewise see that in these 1-second intervals of time, the distance changed by 9.6 or 10.4, and so again, we're not seeing a constant rate of change. But we can still talk about the average speed of the runner, the average rate of change. Let's first talk about the average rate of change over the entire race, from 0 seconds to 10 seconds. In 0 seconds to 10 seconds, the runner has completed the race, so they've run 100 meters. And that 100 meters was run in 10 seconds. So on the one hand, we could say that on average, this runner has had a speed of 100 meters per 10 seconds. But that wouldn't be a conventional way of reporting speed. We like to report speed in per 1 unit of time. So rather than saying 100 meters in 10 seconds, we're going to proportionally break that down into 1-second chunks. So divide by 10 proportionally, and what we see here is that 100 divided by 10 would be 10 meters per second. So on average, the runner has a speed of 10 meters per second over the entire race. Now, here's the intuition I'd like you to dwell on as we go through this video. Does the runner have an instantaneous rate of change that's ever the same as the average rate of change over that entire race? That is the runner's instantaneous rate of change ever exactly 10 meters per second? Let's explore that first using Desmos. So we have seen that the average speed of the runner was 10 meters per second. So what you're looking at in this graph is the graph of the line y equals 10x, representing that 10 meters per second average speed. That is, if you increase time by 1 second, distance increases by 10 meters. 1 second, 10 meters. 1 second, 10 meters. Constant speed of 10 meters per second was this runner's average speed. But we know that in reality, his speed ever increased. When we looked at the change in distance over those 2-second or 1-second increments, we saw that he was accomplishing or traveling greater and greater amounts of distance over the same intervals of time. And so we want to think about, was the runner's instantaneous speed ever the same as his average speed, his average rate of change over this entire race. So what you'll see here in Desmos as I move this slider is you'll see the graph of this increasing distance per unit of time, and that function that we used to model the race was the 0.4x squared plus 6x. And so watch this. As the graph is drawn, you're simultaneously going to see the instantaneous rate of change in green. And what I want you to pay attention to is, when do you think the instantaneous rate of change is the same as this average rate of change we're seeing here in blue? So here we go. So as we see initially, the slope or the rate of change of the curve initially is a little less than that blue average rate of change of 10 meters per second. But as time goes on, as the race goes on from the initial starting line, we start to see that maybe in here we see that the slope here, the rate of change of that actual quadratic curve showing the runner's distance versus time looks like it has the same rate of change as that blue graph. And as the graph continues, as the race continues, now we see that the rate of change is greater than the average rate of change of 10. So back it up. The rate of change is less than 10. The rate of change is maybe equal to 10. And the rate of change is for sure greater than 10. So the question is, does it appear as though the instantaneous rate of change is ever 10 meters per second? And I think we can agree that right about in here, that rate of change in green looks to be about the same as the rate of change in blue. It appears as though the slopes are the same. It appears as though the graphs are parallel at that moment in time, around 5 seconds, halfway into the race. Let's go back and analyze that more symbolically or analytically to confirm what we're seeing on Desmos. So the question at hand is this. Is the runner's instantaneous rate of change ever the same as the runner's average rate of change over the entire race? Over the entire race, the runner's running 10 meters per second. On Desmos, we saw that about midway through the race, around time equals 5 seconds, it appeared as though the runner's rate of change was the same as that 10 meters per second. But let's explore that more analytically and see. What we now know about instantaneous rate of change is we can measure it using the derivative. So in this case, the distance that the runner is from the starting line as a function of time can be a model for this distance function is 0.4t squared plus 6t. Therefore, the runner's instantaneous rate of change, the derivative, using the power rule would be this. 2 times 0.4 is 0.8t, decreasing that power by 1. And then the derivative of 6t is just 6. And so our derivative function would be this linear function, 0.8t plus 6. So again, the question is this instantaneous rate of change for any input value of t equivalent to that average rate of change of 10 meters per second? Well, let's find out. Is 0.8t plus 6 ever equal to 10? We have a nice simple linear function here, a linear equation to solve. We can subtract 6 from both sides. So 0.8t will equal 4. Divide both sides by 0.8. And you can check this out, but if you take 4 divided by 0.8, you do indeed get 5 seconds. So as we predicted in Desmos, at the time exactly when the time of the race is 5 seconds into the race, the runner will have accomplished a speed of 10 meters per second. Now that won't persist. As we see, the runner's speed is always changing, but at that instant, the speed is 10 meters per second, the same as the overall rate of change, the average rate of change over the entire race. Now we can do this for different intervals of time. It doesn't have to be the entire race. So for example, what if we wanted to know how fast was the runner running on average during the last half of the race? So I've repeated the data here from the original data set, that at time 5 the distance was 40, at time 10 the distance was 100. So what would the average rate of change be here? Well, first of all, how far did the runner run in that second half of the race, the last 5 seconds of the race? Well, the runner has gone from the 40-meter mark to the 100-meter mark. So we could subtract to find out that the runner has gone 60 meters in the second half of the race, in second 5 seconds of the race. And that took the remaining 5 seconds, the last 5 seconds of the race. And again, to see that, we could subtract. We could say 10 minus 5 is 5 seconds. So the runner has gone 60 meters in 5 seconds. Again, that's not how we typically report speed. We'll report it in a per 1 unit of time. So we'll divide by 5 to get this to be per 1. 60 divided by 5 is 12. So we will say 12 meters per 1 second. So on average, in the second 5 seconds of the race, the runner runs on average 12 meters per second. So a question could be, is the runner's instantaneous rate of change ever the same as that? Is it ever the same as 12 meters per second? Let's do a quick Desmos exploration and see if we can get a feel for the answer to that question. So we're now focusing on the last 5 seconds of this race. So this linear line segment in blue represents the average speed of 12 meters per second. You can kind of see it here. At time 5, the runner has run, so he's 40 meters from the starting line. 1 second later, it would be 52. Another second later would be 64, et cetera, et cetera, et cetera. We see that constant rate of change, the average rate of change of 12 meters per second for those last 5 seconds until he finishes the race. After 10 seconds, he's gone the full 100 meters. So the question at hand now is there ever a time when the runner's instantaneous rate of change is the same as his average rate of change? So once again, we'll slide the slider to see that quadratic function representing the runner's actual distance versus time, and we'll ask the question, does it appear as though the instantaneous rate of change is ever the same? So in green, you see the representation of the slope of the curve at a moment. And so we'll see right about there, the slope is a little shallow. It's less than 12 meters per second. But that rate of change is ever increasing until maybe right about in there. And what I'm focusing on is how the green line representing the instantaneous rate of change is parallel to the blue line representing the average rate of change, thus having the same rate of change. So it appears as though that happens right around the 7-second mark. Now if I keep going, that rate of change you see becomes steeper than the benchmark there of the 12 meters per second. And so at the end of the race, the runner is actually running greater than 12 meters per second. But there certainly does appear to be a time, maybe around 7 seconds, where the average and the instantaneous rates of change are the same. The slope of that blue line segment is the same as the slope of the green actual distance time curve. That is, the two lines are parallel. Let's go back to the board and analyze this analytically and see if our approximation or estimate of time t equals 7 seconds is accurate. So to answer the question, is the runner's instantaneous rate of change ever the same as the runner's average rate of change? We explored on Desmos to just visualize where is that instantaneous rate of change, the slope of the curve, the same as the slope of that line segment, to see where the two lines appear to be parallel. And it looked like around time t equals 7 seconds. But let's find out for sure. Instantaneous rate of change, the derivative of that function. Remember, the function is that quadratic 0.4t squared plus 6t. And so the derivative of that function, by the power rule again, is 0.8t plus 6. And what we're interested in is, does this derivative function ever have the same rate of change as the average rate of change of 12 meters per second? Let's find out. So again, solving this linear equation, we can subtract 6 from both sides and say 0.8t is equal to, subtract 6, we'll get 6. Divide both sides by that 0.8, and we'll have 6 divided by 0.8. Now, just for dramatic effect, let's think about this for a minute. 6 divided by 0.8. Now, 0.8 is the same as 8 tenths. 8 tenths. It's the same as 4/5. So it's really 6 divided by 4/5, or 6 times 5/4. 6 times 5/4. That's like 30/4. That's not quite 7. That's about 7.5. So while on Desmos we estimated it to be around 7 seconds, the reality is that the rates of change, the instantaneous rate of change and the average rate of change were the same after 7.5 seconds. Now all of this is to get you to think intuitively about a theorem called the mean value theorem. Let's look at the more formal definition, the formal explanation of the mean value theorem. So in 2 examples throughout this video, I've had you think about, are there any moments in time where the sprinter's average rate of change and instantaneous rate of change are the same? This idea is known as the mean value theorem. I'd like to just present it to you a little more formally and just also have you know that this idea is going to be used in future videos. But for now, this intuitive nature of the sprinter's average rate of change and instantaneous rate of change being the same is a good way to start. But more formally, here's what the mean value theorem states. If a function is continuous, so no asymptotes, no holes on the graph, nothing funky going on like that. If a function is continuous on an open interval between a and b, like in the context of our race, that interval would have been between 0 and 10 in the first case, or between 5 and 10 in the second case, but we could have done it on any interval of time in this race. As long as the function is continuous on that open interval and differentiable on the closed interval. So differentiable is this idea, there's no cusps, no sharp points. We can actually compute a derivative by taking the limit from both sides. So basically we're saying there's nothing funny going on. We have a nice behaved function on the closed interval and open interval a to b. Then, guaranteed, there will be at least one value that we're going to call c within that interval such that, now here it comes. Remember how I was having you think about the average rate of change and instantaneous rate of change being the same? Here's how we say this in mathematical notation. The derivative at some location c, like in our first case, that value of c was the 5-second point in the race. In the second case, it was the 7.5-second point in the race. There's going to be some value of c where the instantaneous rate of change is the same as the average rate of change. So clearly, when you saw those examples work through, we took the derivative and we found, for instance, that time equals 5. The value of c we're speaking of here was the 5-second point in the race. Or in the second case, we found that the value of c was the 7.5 second mark in the race. That's where the instantaneous rate of change was the same as the average rate of change. Now, there's a previous video about average rate of change, but just a quick highlight. This is saying at some output, at some input value of b, there's an output. At some input value of a, there's an output. Subtracting finds the difference in those outputs. Like in the first case, 100 meters. In the second case, 60 meters. Divide that by the change in the inputs, in our case, the change in time. The overall 10 seconds in the race in the first case, the 5 seconds in the race in the second case, gives us the average rate of change. And the question was, were those two quantities ever the same? And so we found out. By Desmos, little exploration, little estimation, we found out that they were the same at time equals 5 in the first case, 7.5 in the second case. So this theorem promises us, it's a guarantee, if you have a continuous differentiable function on these intervals, that there will be at least one value such that the instantaneous rate of change is the same as the average rate of change. The mean value theorem.